In this video, we learn a technique called partial fractions. And what we're going to be looking at are integrals that have the shape of some function of x divided by like a product of some other functions, right? And typically we would say like f and g here in a denominator would just be like factors, whether they're binomial or trinomial factors, right? Something like x plus 4 and x squared plus 1. We're going to look at how we integrate something of that shape as long as the function in the numerator has a smaller power than what's in the denominator. Let me give you some examples here. The way this is set up is basically so that we decompose this fraction here, and we end up with a simple function divided by f of x plus another simple function, a different one, not necessarily the same, divided by g of x. Okay, so pretty much everything we do in this section is really just algebra, right? It's what we call partial fraction decomposition. We'll be taking fractions and breaking them up into smaller fractions, and the idea there is, up until this point in math, you basically have been told to condense your fractions, get a common denominator, combine your fractions. We do that a lot of the time, yes. Our goal here, as far as integration goes, we have an easier time integrating small pieces than we do giant combined ones. So the goal for this section is to break things apart and to make use of one of the basic rules of integration, where we integrate du over u and get natural log. All right, that should be a natural log of u there. So what we're going to be doing is breaking apart these fractions and making use of that basic formula. Hopefully, once we decompose a larger fraction, we get pieces that look like du over u, or similar. Okay? So there's going to be a kind of a guideline worksheet posted for you on our course webpage. And basically, this will detail kind of the main scenarios that we'll find ourselves in for partial fractions, okay? So you can read through that on your own. I didn't want to post it here and read through the whole thing, but it's there for you. I did highlight a little bit at the bottom there. In order for this decomposition to work, the degree of the numerator must be less than that of the degree of the denominator, okay? If it's not, if the degree of the numerator and denominator are the same, or if the degree of the numerator is larger than the degree of the denominator, you're probably looking for some long division, okay? Long division then will break things down and hopefully make things easier to integrate then. So what I want to do is actually look at the example at the bottom of the page there. I'm going to rewrite it for you. I want to write the decomposition for this big fraction, x squared minus 9, all divided by x times x squared plus 4 times x plus 5 quantity cubed, and then finally a factor of x plus 1. So I want to describe to you how this decomposition goes, and actually this example will kind of handle most of the what if scenarios, right? So what if my integral has this, how do I decompose? Fractional decomposition is a whole study in itself, and we're just going to take kind of a small subset of those and figure out kind of how the process works and what do we do in a specific situation. So what I'm looking to do here is, say I have the integral of this fraction. I want to decompose the fraction into smaller pieces. What I do is I always look at the factored version of the denominator, right? So I'm always going to factor things out. And to know that I can do this, I have to look at the degree of the numerator and the degree of the denominator. Degree in the numerator is 2, and if I FOIL that denominator out, I'll see a x to the 7th. Okay, so I know that partial fractions here should work out in my favor, and if you're not going to see that yet, that's okay. I look at all the factors in the denominator, and that will kind of determine how the decomposition goes. I see a factor of x, a factor of x squared plus 4, 3 factors of x plus 5, and 1 factor of x plus 1, okay? So I'm going to try to color code all of this. The idea is that I can say that this big fraction is equal to, if I've got a single linear term in the denominator here, I've actually got 2 of those. there, I will end up with a placeholder divided by that linear term. So it looks like this. For x in the denominator there, I'm going to have an a over x. This a is a placeholder. I don't know what right now constant has to go there. Hopefully it's a constant. It has to go there in order for the composition to make sense. We'll get there. This x squared plus 4 is a non-reducible quadratic. Okay, it's a quadratic. The numerator of that term I expect to be 1 degree less. So I assume that that has to have the shape of bx plus c. I already used a, right? So I'm going on to using b. So I have to assume that the numerator is a whole linear piece, bx plus c. Okay. Again, this is detailed on that kind of that sheet posted on our webpage that you can look into a little bit deeper. I'm skipping past some of that. The x plus 5 quantity cubed is interesting. It's linear. X plus 5 is linear anyway, but when I cube it, it becomes a cubic. Okay, what makes us think we have to do something like a bx squared plus cx plus d? Kind of. What we call this is a repeated linear factor. So it's got a power of 3. So what this is going to result in is 3 different placeholded factors, all of which having 1 power of that factor, right? So there's 3 x plus 5s. So I'm going to have 3 terms that come from that. D over x plus 5, E over x plus 5 squared, and F over x plus 5 cubed. Okay. Last but not least, there's non-repeated, and it's reduced as far as it can go. It's a linear term, x plus 1, and that's just going to give me another factor. I'm at g now, g divided by x plus 1. Okay. So that's how I decompose some big fraction, some quotient like this, is when I can factor the denominator as much as I possibly can, and I try to determine what types of factors I have. Do I have linear factors? Do I have quadratic factors? Are they reducible? Can I factor them more? Do I have repeated factors? And all of those things will yield a different placeholder, right? So study that sheet and on the previous slide, and hopefully you'll get a better idea of what type of factor I choose when. So that's half the battle. Once you find your decomposition, the main goal will be to determine what A, B, C, D, E, F, and G are, to determine those placeholders. Okay, we'll go through that process in just a second, but I want to say some things here. It doesn't matter what the numerator is, at least not yet. Okay, we will use the numerator to help figure out what those placeholders are. But as far as the decomposition goes, I didn't care what was up here, x squared minus 9, in order to figure out all of these factors here. It doesn't matter, okay? Also, the decomposition depends on the factors in the denominator, right? So I want things to be in most factored form. And finally, in order for this to work, I need the degree of the numerator to be smaller than the degree of the denominator. Okay, if that's not the case, you're looking to go back and try some other technique, probably long division. I want to do at least 3 examples here where I kind of outline some different scenarios and try to incorporate as many of these types of decompositions as I can. Here's the first. I want to rewrite 1 over x squared plus x with the decomposition, and then use that to evaluate this integral, dx over x squared plus x. Okay, so this integral, by the other means that I know right now, I don't have a good way to evaluate it. There may be some other way with some algebra that I'm not thinking of, but I do notice that I can factor 1 over x squared plus x to 1 over x times x plus 1. Okay, I've got 2 linear factors here. None of them are repeated. Neither of them are repeated. And they're both as factored as I possibly can be. So what I'm going to get from that when I decompose this fraction is 2 different terms. Each of these terms will have exactly the same denominators, right? I'll have a denominator with x and a denominator with x plus 1. And all I need, because these are linear factors, is just a single constant placeholder in each of the numerators. I choose a and b. Now the order of which you do this doesn't matter. So if you said it was a over x plus 1, that's okay. You're going to get different a and b values than I will here, but the whole integral will work itself out so that you'll get the same answer, okay? Or you should get the same answer. So what we do, what's left, is to figure out what a and b are. I've got to work backwards a little bit to figure out how these two smaller fractions combine together to give me 1 over x squared plus x, okay? And it's not necessarily an obvious thing, but the basic idea of how this works is we kind of treat it like we would find a common denominator, right? If I actually go ahead and add those two fractions, a over x and b over x plus 1 together, what would a and b have to be so that the result on the left side would be 1 in the numerator? There's kind of a clever way to do this. What we do is we take the fraction and we clear all fractions here. And what that results in is taking the common denominator and multiplying it through. So I've got brackets around what I'm going to multiply that common denominator through. So I take the whole thing, that whole equation, and multiply through by x times x plus 1. That's my common denominator. On the left side, I multiply 1 over x times x plus 1. I multiply that by x plus 1. So the only thing that's left is the numerator here, which is 1. So the numerator does come into play. It does matter what is in that numerator. I'll show you some examples soon, where we actually have something that shows up that's not just a 1 there. On the right side, I've taken a over x and multiplied it by x times x plus 1, right? X parentheses x plus 1. The x's are going to cancel, and I'm left with a times x plus 1. One more term to multiply into. I distribute x times x plus 1 times b over x plus 1. We see the b remains, the x remains, but the x plus 1's cancel, and I'm left with bx, okay? From here, I've got just a nice little equation and kind of three unknowns, right? X, a, and b. So I need to figure out what a and b are so that I can write then my decomposition here. And there's a clever way to do this. Basically, we choose x's strategically so that we're able to find these placeholders a and b. Okay? There's a couple different ways to do this, but one of the main ways we like to use is we choose x so that I can hopefully eliminate one of my unknowns. X can potentially be anything. So what I'm going to do is choose x so that I hopefully eliminate a and b. Not simultaneously, but one at a time. So what I do is I look at the factors, right? I look at x plus 1. What would x have to be to make that disappear? Would have to be minus 1. Let x be minus 1. If that's the case, then the left-hand side is a 1. The right-hand side, I've got a times minus 1 plus 1. I've got a times 0. That's a 0. And then I've got plus b times minus 1. So all of this, when I choose x to be minus 1, I've got negative b equals 1 or b equals negative 1. I've got one of my values from one of my placeholders. Okay? Kind of clever. Kind of cool. Then I find the other placeholder by choosing a different x value, hopefully, so that I eliminate b but keep a. What x value would you choose? Well, what is being multiplied by b? It's x. To eliminate b, I would let x be 0. So when I let x be 0, I've got 1 on the left again. A is multiplied by 0 plus 1, and b is multiplied by 0. So all of this gives me a times 1, or a equals 1. Okay? I'm almost done. I figured out that I can write my fraction here, 1 over x times x plus 1, as a over x plus b over x plus 1. And I now know what a and b are A is 1, B is minus 1. And all that's left to do is integrate everything with respect to x. Okay? So I take that decomposed fraction and I integrate everything with respect to x, and that's going to give me the integral of my original fraction. Okay? I'm going to slide over to the next slide here and integrate. I've got 1 over x dx. That integral should become natural log of absolute value of x plus the integral of minus 1 over x plus 1. I can do a quick u sub. I don't even really have to. I'm going to get a natural log from that as well. If u was x plus 1, du would be dx, and my integral would end up like minus du over u. That's going to give me a minus natural log of x plus 1 plus c. Very frequently, because we end up with a lot of natural log components here, we often use those log properties to bring things together, kind of reconsolidate. So instead of writing natural log of x minus natural log of x plus 1, we can condense that to natural log of x divided by x plus 1. Okay, so that's something we do rather frequently. It's not required, so I don't want you to think every time you've got to remember those log properties, but if you're looking your answer up or checking your work online or in the textbook, you might see an answer that looks different than yours. So think about those log properties. That's probably how they did that. Let's do another example. Here I've got 5x squared plus 20x plus 6 divided by x cubed plus 2x squared plus x. Okay, so I'm going to go through the same process a little bit quicker here. The first thing I notice is that the degree in the numerator is indeed smaller than the degree in the denominator. That's good. So that means I should be able to decompose things here and get something that's beneficial with partial fractions. So I'm going to factor the denominator. I see there's an x in common. Ooh, skipped a bunch. There's an x in common. So I factor that out, and then I notice what's left, x squared plus 2x plus 1, factors to x plus 1 squared. So my denominator I can write as x times x plus 1 quantity squared. So to decompose this, I pay attention to the denominator, and I see that I've got a linear factor of x and a repeated factor of x plus 1. Okay, so I know that repeated factor, there's some intricacies with that. But my fraction, I can say the x in the denominator is going to have just a single placeholder, a over x. Okay? The repeated factor has two terms that go along with it. A over x plus 1 and b over x plus 1 squared. I've already got a, so we go right to b over x plus 1 plus c over x plus 1 squared. Okay? And the reason that is in order to bring those together to get a third degree, I have to have kind of all of those kind of possibilities. We can't just assume that it's just c over x plus 1 squared. There's a possibility that it's also b over x plus 1. So we have to consider that as one of our terms in the decomposition. You'll get used to it. So all that's left is to find these placeholders and then integrate. I do the same thing as before where I cancel my fractions. I clear everything by multiplying through by the common denominator. Okay, so my common denominator is always going to be given, right? It's going to be the denominator of your integrand, what you're integrating. I distribute that common denominator through, and I end up with, again, on the left side, whatever's in the numerator of my original fraction. Right? So in the last example, it was 1. In this example, there's something up there that's going to remain, right? 5x squared plus 20x plus 6. I don't really care that that's factored. Again, it doesn't really matter what the numerator is. Just know that it's used in finding the placeholders when you're clearing your fractions here. You don't need to factor it if you don't want to. All that we're going to be doing is plugging in x values. Okay? So when I distribute then the common denominator to the right side of my equation, I'm multiplying a over x by x times x plus 1 squared. The x's cancel, and I'm left with a times x plus 1 squared. Plus, when I distribute to the middle term, b over x plus 1, one of the x plus 1 terms cancel. There's an x and an x plus 1 left over. And lastly, when I distribute to the third term, the x plus 1 squareds are going to cancel, and I'm left with just cx. Okay? I'm going to move over to the next slide here, but all that's left is to figure out what a, b, and c are. So all that I have to do is strategically choose x values so that hopefully I end up with a, b, and c. So here's just a rewrite. I'm going to choose x values, again, hopefully eliminating some factors and keeping others, right? So the first thing I notice is that I can choose x to be minus 1 again. When I do that, the left-hand side, I plug in minus 1 for x. So I've got 5 times negative 1 squared is 5, plus 20 times minus 1 is 5 minus 20 is a negative 15, plus 6 should give me a negative 9. On the right side, when I plug in minus 1, both the terms next to or with a and b are going to disappear, right? I've got 0 next to a, 0 next to b, but my c is multiplied by a minus 1. So then I can say that c is just, that should be a positive 9, I believe. C should be a positive 9. Sorry about that. So I figure out C. I have A and B left over. The next logical choice for X is to let X be 0, because that will eliminate C. But it will also eliminate B, leaving me with just A. On the left side, I have a 6. On the right side, I've got A times 0 plus 1, and there's a 0 next to B and C. So all that's left is A to be 6. Okay? How do I figure out B? Well, it's a little tricky because I've chosen the x values that would make the factors that I have disappear. Because of this repeated factor, that's going to disappear and not be left over when x is minus 1. So basically what I'm stuck with is to choose some other x value. It can be any x value. But to use what I already know 2 of the placeholders, I will be able to eliminate then my other unknowns and be just left with b. So we pick some other x value. You can choose anything. I'm going to choose 1 because that's easy to plug in. Okay. So I plug in 1, I get 5 plus 20 plus 6 is a 31 equals, next to a, I've got 1 plus 1 squared, so that's 2 squared is 4a, plus b times 1 times 1 plus 1 is 2 times 1 times b is 2b, plus c times 1 is just a c. And again, I know what c and a are, so I've got 31 is equal to 4 times 6 is 24, plus 2b plus c is plus a 9. So this should be plus a 9. Okay. When all is said and done there, I subtract 24, and I've got, what does that give me? A negative 7. And then I subtract 9, and somehow I end up with a wrong value. That should end up being, sorry about that, my value for B is actually correct, right? It's a negative 1, and that's because I end up with 7 minus 9 is a negative 2 on the left, and that's equal to 2B. So when I divide by 2, I get B is equal to minus 1. Sorry about that confusion. So I've got my placeholders. I'm ready to then plug things back into my integral. And the way things will go is I've got the original integral, and I write my placeholders. I've taken this from the previous slide, so if you forget where that came from, go back a page. And I'm going to integrate everything once I plug in what A, B, and C are. So I know A is 6, C is 9, and B is a negative 1. So the only thing I've got to change is this should be a positive 9 here. Okay? integrate each one of those. Integrating 6 over x, I should get 6 natural log of x. Easy enough. Plus, integrate negative 1 over x plus 1. That's going to be a minus natural log of x plus 1. Plus the integral of 9 over x plus 1 squared. Be careful here because the integral of 1 over x plus 1 squared isn't natural log of x plus 1. If you do a substitution, if u is x plus 1, du is dx, and you end up with u to the minus 2. Integrate that, you'll get negative u to the minus 1. So I should get a negative 9 u x plus 1 to the minus 1. Okay? Plus a constant. And I've got my antiderivative. I didn't bring this one together. I didn't use my log properties to simplify that, but you have it nonetheless. So just be careful. It's for a lot of these you get natural log antiderivatives, but not all the time, right? We notice that this guy here has an antiderivative that's not natural log. So we just have to be a little bit cautious. Let's do one more. I've got 8x cubed plus 13x divided by x squared plus 2 quantity squared, and I'm integrating all that with respect to x. It doesn't quite look like it, but in the denominator I've got a fourth power, right? X squared squared. So indeed the denominator is a higher power than the numerator. I've got x squared plus 2 as a non-reducible quadratic factor, right? And it's repeated, okay? So the way we break this up is we have to use a degree less, right? So in our numerators, there's going to be 2 because our factor is repeated twice. It's squared. So we've got 2 fractions that this breaks into, and each of them is going to have a linear factor in it. Instead of a constant factor, an a or a b, there's going to be linear factors, ax. So what we see is that x squared plus 2 as a denominator is going to give me a numerator of ax plus b. And then the next denominator, x squared plus 2 squared, gives me a factor of cx plus d. Okay? Because those are non-reducible factors, they have to have linear, 1 degree less of a factor in the numerator, right? So that's where the ax plus b and the cx plus d come from. And there's 2 of them because the power in the denominator is 2, right? Because I've got a repeated factor. The process really after this doesn't change much, okay? I'm going to do it a slightly different way, but really the idea is the same. I need to find these placeholders A, B, and C, A, B, C, and D. So just like before, I'm going to clear fractions. I'm going to multiply through by my common denominator everywhere. We know on the left side, I'm going to get the numerator of the whole thing. All right, so I'm doing something that's on the side, right? This isn't still an integral form. I'm just looking at the insides of everything. So when I distribute my common denominator, on the left, I have 8x cubed plus 13x. On the right, I've got ax plus b times a factor of x squared plus 2. Both of those factors didn't disappear. However, on the next term, the second term, next to cx plus d, both factors of x squared plus 2 disappear, and I've got just a cx plus d here. Okay? So that's what I get when I clear these fractions. Again, all just algebra. And what's left to do is still find A, B, C, and D. Okay? You'll notice that if I try to choose x values here, I get kind of stuck pretty quick because there's no way that I can eliminate x squared plus 2. X would be like, what? Square root of negative 2? And I can't really do that. X is supposed to be a real number. So what we like to do in a situation like this is what we call equating coefficients. I want to see if I can use the right-hand side matched up with the left-hand side to come up with what's in front of the x cubed term and what's in front of the x to the first term. So what I'm going to do is I'm going to take everything on the right-hand side here and I'm going to FOIL it all out. And then I'm going to collect powers of x. to match with the left-hand side. I could have done this in the examples before. I just kind of chose not to. So when I distribute all this, I end up with an ax cubed plus bx squared plus 2ax plus 2b, and of course then plus 2c plus d. And I'm going to collect this in a way so that I get all the powers of x's together. So on the right side again, I've got ax cubed plus bx squared plus 2a plus c times x, right? Those are both x terms. And then 2b plus d is going to be my constant term. So I'm just going to collect those and bring them together. So now it's just a matching game. I look at the left side, and what's in front of the x cubed should be the same. A has to be 8 in order for those things to be equal. What's in front of the x term, 13, has to be what's in front of the x term on the right. So in order for this equal sign to make sense, 13 should be equal to 2a plus c. Well, I know what a is 8. So I've got 16 plus c is 13, so c should be a minus 3. I've got a and c just by a quick matching. On the left side, I don't have any x squared terms. So on the right side, b then should be a value to eliminate x squared. B should be 0. And in fact, 2b plus d should also be 0 because there's no constant term on the left side. So both b and d, I can argue, would be 0 here. Okay? So again, this is what I call, matching coefficients. And it's just a quick little, usually pretty quick. Since I didn't have a lot to multiply out on the right-hand side, then this was a relatively friendly method to use. Sometimes over here you've got a lot more to multiply, and that's what makes this method a little bit uglier. So I'm going to rewrite my integral then. I know that a is 8 and b is 0. So that first fraction I get 8x plus 0, or just 8x in the numerator. The second fraction, c is a negative 3 and d is 0, so I've got just a negative 3. Okay, all that's left to do is integrate. And hopefully I'm to a point where I can do these integrals with hopefully little work. In fact, both of these guys are substitutions. If u is x squared plus 2, in either case, I can substitute and end up with an integral that I can do with one of my basic rules. Okay, the first one does happen to be a natural log. I'll have 4 natural log of x squared plus 2 minus 3 times the integral of x over x squared plus 2 squared. Okay, this one, because there's not just it doesn't result in a du over u, it's going to result in a du over u squared. So the antiderivative isn't a natural log here. It's going to give me a u to the minus 1. So when I bring everything back in, it's a minus 3/2 x squared plus 2 to the minus 1 divided by the new power divided by another negative. So that's why they see a plus sign in between. Okay. There's my antiderivative. This is basically how partial fraction decomposition goes. So I've showcased kind of 3 different examples here. By no means have I done all the possible examples that you can do. There are some that are much easier. There are some that are much harder. I tried to give a nice little overview. Sometimes this matching coefficient method is a little bit better, and that's usually reserved for when I can't choose x's strategically, okay? But in general, we look for a numerator that's smaller in power than the denominator. We then factor the denominator and figure out what the decomposition of that fraction would be. Use that sheet as your guide in order to figure out what the decomposition should look like. That's probably the hardest part. After that, it's all just this game about figuring out what the placeholders are. Once you do that, the integrals should mostly be straightforward. You've either got some powers of u or some natural log pieces that are left over. Okay, that's all for this video. Thanks for watching.